Welcome to G Fun Facts Online. Today, we're rewriting the rules of the universe. For centuries, we thought of gravity as an invisible rope, a mysterious force pulling objects together across the void of space. Isaac Newton gave us the math for this rope, but even he couldn't explain how it worked. Then came Albert Einstein, who didn't just offer a new explanation for the rope. He declared there was no rope at all. In Einstein's universe, gravity isn't a force. It's the shape of reality itself. It's a consequence of the very fabric of space and time being curved. This is the story of how our understanding of the cosmos was fundamentally reshaped, a journey from invisible forces to a universe carved from curves. Before we can appreciate the genius of Einstein's idea, we need to understand the world he started with. In 1687, Isaac Newton published his laws of motion and universal gravitation. His law was a triumph. It described how every object in the universe attracts every other object with a force proportional to their mass and inversely proportional to the square of the distance between them. It explained why apples fall and planets orbit. For over 200 years, it was the bedrock of physics. But it described a universe where space was a static, flat and unchanging stage. Time ticked by at the same rate for everyone, everywhere. And gravity, this mysterious force, acted instantaneously. If the sun were to vanish right now, Newton's theory said the Earth would instantly fly off its orbit. This idea of action at a distance bothered many, but it became a huge problem for Einstein. His 1905 theory of special relativity had established a universal speed limit, the speed of light. Nothing, not even information, could travel faster. This meant the gravitational effect of the sun disappearing couldn't reach Earth instantly. It would have to take at least 8 minutes, the time it takes for sunlight to reach us. This fundamental conflict was a crack in the foundation of physics. Newton's gravity and special relativity couldn't both be right. A new theory of gravity was needed. The journey to that new theory didn't start with dense equations, but with a simple mental image that Einstein later called his happiest thought. In 1907, he imagined a man falling from a roof. He realized that while the man was falling, he would feel weightless. If he emptied his pockets, the objects would float alongside him. In his own little bubble of reality, gravity would seem to have disappeared. This led Einstein to his equivalence principle. The effects of gravity are completely indistinguishable from the effects of acceleration. To grasp this, let's use another of Einstein's famous thought experiments. Imagine you are in a sealed, windowless elevator. In the first scenario, the elevator is resting on the surface of the Earth. You feel your weight pressing you into the floor. If you drop a ball, it falls, accelerating downwards at 9.8 meters per second squared. We call this gravity. Now for scenario 2. The elevator is in deep space, far from any planets or stars. A rocket attached to the top fires, accelerating the elevator upwards at a constant 9.8 meters per second squared. Inside, you would feel the exact same sensation. Your feet are pressed into the floor with the same force. If you drop a ball, the floor of the elevator rushes up to meet it, and from your perspective, the ball appears to accelerate downwards at 9.8 meters per second squared. From inside that box, there is no experiment you could possibly do to tell the difference between being stationary in a gravitational field and accelerating in empty space. This equivalence was the key. It implied that gravity wasn't some external force acting on objects, but was somehow woven into the very fabric of spacetime, the four-dimensional framework that combines the 3 dimensions of space with the 1 dimension of time. If gravity and acceleration are 2 sides of the same coin, and acceleration creates curved paths through spacetime, then Einstein realized gravity must be the curvature of spacetime itself. This was a monumental conceptual leap. But to turn this physical intuition into a mathematical theory, he needed a new language, one that could describe curved spaces. For thousands of years, our understanding of space was based on the geometry of Euclid, the kind we all learned in school. In this flat world, parallel lines never meet, and the angles of a triangle always add up to 180 degrees. But in the 19th century, mathematicians like Carl Friedrich Gauss and his student Bernhard Riemann began exploring the geometry of curved surfaces. Think about the Earth. It's a sphere, a curved surface. If you and a friend start at the equator, 1,000 miles apart, and both walk due north, you start out on parallel paths. But as you approach the North Pole, you will get closer and closer until you eventually meet. Your parallel lines have converged. If you draw a giant triangle on the Earth's surface, say from the equator to the North Pole and back down, the sum of its angles will be more than 180 degrees. This is the world of non-Euclidean or Riemannian geometry. It was this abstract mathematical framework, developed 60 years earlier, that provided exactly the tools Einstein needed. He proposed the universe is a four-dimensional manifold. A manifold is just a space that looks flat on a small scale but can be curved on a large scale. Just like a small patch of ground on Earth looks flat, but globally, the planet is a sphere. In Einstein's theory, the presence of mass and energy warps and bends this four-dimensional spacetime manifold. To describe this mathematically, Einstein, with the help of his mathematician friend Marcel Grossmann, adopted the language of tensors. The most important of these is the metric tensor. You can think of the metric tensor as the rule book for geometry at every single point in spacetime. It's a collection of numbers that tells you how to measure distances, angles, and volumes in a potentially curved space. In a very real sense, the metric tensor is the gravitational field. It contains all the information about the curvature. So if spacetime is curved, what happens to the idea of a straight line? In a curved space, the equivalent of a straight line is called a geodesic. It's the straightest possible path an object can take. Imagine an ant walking on the surface of an orange. If the ant walks straight ahead without ever turning left or right, its path from our three-dimensional view is a curve. But from the ant's perspective, it's following the straightest line possible on that curved surface. This is the central idea of general relativity. Objects in freefall, that is, moving only under the influence of gravity, are simply following geodesics through curved spacetime. The Earth is not being pulled by the Sun. The Sun's enormous mass creates a deep curve, a sort of valley, in the fabric of spacetime around it. The Earth is simply rolling along the straightest possible path within that curved valley. From our limited three-dimensional view, we see this path as a nearly circular orbit. Gravity isn't a force that makes things deviate from straight lines. Gravity is what defines the straight lines in a curved universe. And what tells us how much spacetime is curved? Another mathematical object called the Riemann curvature tensor. This tensor has a direct physical meaning. It describes tidal forces. Imagine two astronauts floating side by side in space, both falling towards the Earth. Their paths are geodesics, both aimed at the center of the Earth. As they fall, those paths will converge, and the astronauts will see themselves drift closer together. If one is slightly above the other, the lower one accelerates faster, and they will drift apart. This stretching and squeezing effect is the tidal force, and it is a direct physical manifestation of spacetime curvature. If the Riemann tensor is zero, spacetime is flat, and free-falling objects don't drift towards or away from each other. If it's non-zero, spacetime is curved. With all this mathematical machinery in place, Einstein unveiled the heart of his theory in 1915, the Einstein field equations. In their most compact form, they look deceptively simple. G_mon equals a constant times T_mon. But this is actually a set of 10 incredibly complex, interlocking equations. It's a cosmic dialogue, famously summarized by the physicist John Archibald Wheeler as "Spacetime tells matter how to move. Matter tells spacetime how to curve." Let's break that down. The right side of the equation, T_μ is the stress-energy tensor. It represents all the matter and energy in a region of space, its density, its pressure, everything. This is the matter tells spacetime how to curve part. You input the distribution of stuff, and the equation tells you what happens next. The left side of the equation, G_μ, is the Einstein tensor. This is a purely geometric object built from the metric tensor and its derivatives. It describes the resulting curvature of spacetime. This is the spacetime tells matter how to move part. Once you know the curvature, you can calculate the geodesics, the paths that objects will follow. The equal sign is the revolution. It forges an unbreakable link between the contents of the universe and the geometry of the universe. A beautiful theory is one thing, but a scientific theory must make predictions that can be tested. And general relativity's geometric view passed with flying colors. For decades, astronomers had been puzzled by Mercury's orbit. Its elliptical path around the Sun wobbles, or precesses, at a rate that couldn't be fully explained by Newton's laws. When Einstein applied his equations, the predicted precession from the Sun's curvature of spacetime matched the observed anomaly perfectly. It was the theory's first stunning success. Next, Einstein made an even bolder prediction. If gravity is curved spacetime, then it should affect everything that travels through it, including light. He predicted that light from a distant star passing near the Sun would have its path bent by a specific amount. The only way to test this was during a total solar eclipse, when the Sun's glare is blocked. In 1919, an expedition led by Sir Arthur Eddington photographed the stars near the eclipsed Sun. The results were clear. The starlight was bent, exactly as Einstein had predicted. This confirmation catapulted Einstein to global fame and cemented the geometric view of gravity. This light-bending effect, when caused by a massive galaxy or cluster of galaxies, is called gravitational lensing. The immense gravity can act like a cosmic magnifying glass, creating distorted or multiple images of objects behind it, allowing us to see galaxies that would otherwise be too faint. The equations also allowed for extreme solutions. If you cram enough mass into a small enough space, the curvature of spacetime becomes so intense that it tears a hole in reality. A region is formed from which nothing, not even light, can escape. We call these objects black holes, the ultimate manifestation of warped geometry. Perhaps the most mind-bending prediction was that accelerating massive objects, like two black holes spiraling into each other, would create ripples in the very fabric of spacetime. These gravitational waves, propagating disturbances in spacetime geometry, would travel outwards at the speed of light. For a century, they remained purely theoretical. Then, on September 14, 2015, the LIGO Observatory made the first direct detection of gravitational waves. The signal came from the cataclysmic merger of two black holes over 1 billion light-years away. For the first time, we could hear the vibrations of spacetime itself, a direct confirmation of Einstein's geometric universe. Today, general relativity is the foundation of modern cosmology. It describes the Big Bang, the expansion of the universe and its ultimate fate. The overall geometry of our cosmos, whether it is curved like a sphere, a saddle, or is perfectly flat, is determined by the total amount of matter and energy within it. Observations suggest our universe is very close to flat, but with a shocking twist. Its expansion is accelerating. This has led to the idea of dark energy, a mysterious property of space itself that pushes the universe apart, a phenomenon that fits neatly into Einstein's equations as a cosmological constant. But for all its success, general relativity has a dark secret. It lives in peaceful disharmony with the other great pillar of modern physics, quantum mechanics. General relativity describes a smooth, continuous, predictable world on the large scale. Quantum mechanics describes the world of the very small as choppy, probabilistic, and fundamentally uncertain. The two theories clash violently in the places where their domains overlap, at the center of a black hole or at the moment of the Big Bang. At these singularities, relativity predicts infinite density and infinite curvature. The math breaks down, the smooth geometry shatters, and we know that a new, more fundamental theory is needed, a quantum theory of gravity. The quest for this theory is the greatest challenge in physics today, and it forces us to once again reimagine geometry. One leading candidate, string theory, proposes that fundamental particles are tiny vibrating strings. Different vibrations correspond to different particles, and one particular vibration gives you the graviton, the quantum particle of gravity. But for the math to work, string theory requires extra, hidden spatial dimensions, curled up so small we can't see them. In this view, the universe's geometry is far more complex than we perceive. Another approach, loop quantum gravity, tries to quantize spacetime itself. It predicts that space isn't a smooth continuum, but is made of indivisible atoms of volume, woven together in a network. From a distance, this pixelated spacetime looks smooth, just as a TV screen looks smooth from your couch. In this view, there might be no Big Bang singularity, but a big bounce, where a contracting universe reaches a maximum density and rebounds. From Newton's invisible force, to Einstein's curved spacetime, to the quantum, pixelated geometry of tomorrow's theories, our understanding of gravity has always been a story about the changing shape of reality. Einstein's revolutionary insight was to see the universe not as a machine governed by forces, but as a magnificent, dynamic sculpture, carved from the very fabric of space and time. This geometric idea has been tested and confirmed for over a century, and it continues to guide our exploration of the cosmos, from the dance of planets to the echoes of creation itself. The quest continues, driven by the enduring power of one of the greatest ideas in human history, that gravity is simply geometry.